In the previous video we talked about poles, and then in the previous videos we talked about the zeros and things like that. And the trend are being shown in this summary is that the zeros move in the clockwise direction, and then the poles goes in the anti-clockwise direction, or the counterclockwise, I would say. Okay, and then the angles, the similarity between the zeros and the poles is that the angles don't change during the mapping process. Alright, from the S domain to the transfer function domain. Okay, and therefore in and the S plus A is simply the translation from the S domain to the, is just to translate the S domain into the how many movement of A, right? Something like that. Okay, you just go back to watch the video if you don't understand what I mean. Okay, but anyway, so while the poles itself, the S plus A talks about the translation, or the 1 over r constant, if you remember back to the previous video, is to enlarge or minimize the radius, that's all. Alright, you can enlarge or minimize the S domain. So we're gonna utilize all this concept that we have found in the past things to build up our understanding on poles and zeros, meaning we're gonna combine now with zeros and poles, and finally to understand exactly what the eventually the Nyquist-Table criterion. And in order to start, we have an example. Okay, this example talks about a 0 and a 2 poles. Alright, if you were to translate it to here, okay, a 0 and 2 poles. We know that from the past videos, we know that the zeros, if you were to, for example, the transfer function of S plus A, G of S is equals to S plus A, and then in the S domain, we have this plot over here, right, this contour, while the zeros is being plot over here, minus A. And then if you were to translate in A direction, you're bringing this point to here, right? This A may be also here, alright? This may be within this loop, it can be anywhere. This minus A can be here, anywhere, as long as it is in the contour. Alright, so I translate into origin over here. Or in other words, I'm translating this point to this point. I'm translating this point to this point. Right, and we call this the mapping, correct? While the angle from this one, for example, I want to find the angle from this point, maybe to this point. This angle is the same as this angle to this angle. Okay, we actually show you. Alright, now and that we also prove that these angles and this angle is the same for poles and zeros also. Alright, the angles don't change at all. So when we utilize this into our current case right now, because we know that the poles and the zeros, the angles don't change, we gotta sum the angles together, right? So this pose, this zero has a certain clockwise angle, while this pose has a certain anti-clockwise angle. And if you were to sum them up together, as you can see, this is the stuff. I'll not go through much into that. When you find the angles, alright, eventually this is something like that. Alright, the sum of the angles. This is this, or perhaps this one. Okay, or in other words, you see, this thing is in the S domain, alright? Or in other words, it's the same as this one. And then while this one transfer function domain is when you sum out all the zeros and the poles together, right? So this plot, as you can see, the distance, the angle between this point and this point, this pole, is this angle. The distance between this 0 to this point is this angle, and then this one to this point is this angle. And then if you were to sum them up together, you will have this one over here. It's just that manner, like last time you learned the Nyquist plot like that. Okay? If you haven't learned the Nyquist plot, then or you forget what is the Nyquist plot, then simply this is just a summation of the angles, that's all. Alright? From, let's say if I want to take this point, I want to map this point. Alright, if I want to map this point to this point. Alright, previously when we say that when we want to map this point to this point, it's just straight away mapping because the angles are the same, right? Because it's just a pure zero system. However, we are talking about interactions between zero and poles, the angle may be changed, and therefore when you map, things start to get complicated, and this point over here will be mapped onto this side when zeros and poles interacts. You get what I mean? So eventually when you plot this the rest of this contour, you have other shapes starting to go out. Alright, you have certain other shapes that goes with it. Alright, and as you can see, this is the plus, this is the minus, this is the minus. The plus is because it is going in the clockwise direction. This one is in terms of going in the anti-clockwise direction. And because this angle is larger than this angle, the anti-clockwise is more than the clockwise. This is why this thing is moving in the anti-clockwise also. You get what I mean? This is for the just plain examples. And x plus 1 and x plus 3, if you take a look, is simply the poles itself. Poles contribute the anti-clockwise direction. The zero contribute the clockwise direction. So this explains the angle portion and in terms of the mapping itself. Okay? Just to show you, I'll just click this thing.
In this video, we show mappings from S to L of S when L of S has multiple poles and zeros. The path S is still a circle of radius 5, traveling in the clockwise direction as before. In this first example, L of S has two poles at S equals -1 and S equals -3 and a 0 at S equals -2. All of these are encircled by the path in S. As the path in S traverses a circle, the angles to the zeros in L of S are shown in pink, and the angles to the poles are shown in blue. The angle between the origin and L of S on the right-hand side is simply the sum of the angles to the zeros, the pink arcs on.
I believe that you may not understand what he says, but in terms of the movement of the angles, I think you most likely know what he's trying to say. It's just moving the angles. It's just a summation as what I've said earlier, okay? So each of the points are being mapped in terms of their angles, and that's all. The angles, this is why we say that we're gonna exploit the angles of the poles and zeros, because they don't change during the mapping process. Alright? And therefore now let's start off with an example by using this configuration. And you may find this familiar, but please do not take this definition as the Nyquist definition. Okay, this is totally different from the Nyquist definition because of the language they have used. Alright, this, I'm not talking about English or Chinese or Korean or what. I'm talking about in terms of the S contour on the GS domain. Okay, later on we'll change these names to certain names that is related to Nyquist. But at this current point right now, let's use this one first, so that you'll get a concept of what is this equation being used for. Okay, and therefore this is the example that we're gonna tackle. We know that there is a 1 0 over here and there is two poles over here. Alright, and by this equation, the number of 0 encircled by S contour. S contour is simply the contour in the S domain. Alright, in the S domain plot, the contour is simply the one that we have been always using, this circle over here. This circle is called the S contour. Okay, I hope this is pretty much straightforward. And the number of 0 encircled by this contour, alright, this contour is simply 1. Alright, because as you can see, there is only one circle encircled inside. This is where you plot your poles and zeros, correct? So this is the reason why you plot your poles and zeros. If you by far you don't understand why do I plot all these things inside, now you finally know something. Alright, and therefore it's equals to, alright, n, let's skip the n first, let's talk about the pole. The pole is the number of poles, the p is the number of poles encircled by the S contour also. So although we have two poles over here, right, but this S contour only encircled one of the pole. The other pole is not encircled. So by far, this means that z is 1, because the number of 0 encircled by the S contour is 1, right? And then the number of pole encircled by this contour is also 1. Correct? And this means that n is simply 0. and n itself is the number of clockwise encirclement in the origin of the GS domain. The GS domain is the transfer function domain, which is this one, and there is no encirclement on the origin. It doesn't do that, right? As you can see, it's actually like that. And therefore, as what you can see, this is in fact stable, right? Because there is no, the number of poles and the number of zeros are same, in the contour itself. So what you have been plotting right now, you are just plotting this contour, all of this information at each of this point, any point in this contour, you plot it over here, you plot it all over here, and therefore this is it. Because you didn't actually plot this thing. If you didn't plot this thing, definitely you will not have anything over here, right? This is the meaning of that. Okay? So it's the number of poles and the zeros inside the contour itself that matters. And therefore, let's do another example. From here, this is similar thing. You have a one zero, sorry, and two poles. However, when you plot this S contour, alright, this S contour is the same S contour as we talked about. And if you happen that you forget, this S contour is equals to 5 EJ theta. We're still talking about the R is equals to 5. That very first video example, we are still talking about it right now. Okay, no joke. Alright. So we are talking about only when R is equals to 5. If R is equals to 7, then you will cover a huge radius which can encompass the number of poles over here. Alright, that's the meaning. But since we are using only 5, let's continue first. Alright, so we're talking about only encircling this 0 over here. So when you have a 0 that is encircled inside this S contour, this means that I have 1 0 or 1 Z over here. This is by the definitions itself, right? The number of 0 encircled by the S contour. Okay? And then we have no poles which is encircled inside, right? And therefore we can simply say that this P is equals to 0. And therefore N is equals to 1. And N is the number of clockwise encirclement in the origin or on the origin in the GS domain or the transfer function domain. What I mean is that I have a clockwise. I'm going in the clockwise direction that encircle this origin. This is the origin, and it's gonna go one loop. It encircle it. Alright, like Matiam encircle, encircle. More examples, then you'll get more better. 1 0 2 poles. And then when I plot the zeros and the poles over here, alright, when I plot all this, I will see that these 2 poles are inside this S contour, and there is no 0. This 0 is outside the S contour, and therefore I can say that Z is equals to 0, P is equals to 2, and therefore N is equals to minus 2. That's because that's a 0. If I bring this P, which is plus 2, over the other side, it will become minus 2. So minus 2 is equals to N. Alright, and since N is equals to minus 2, where N is a clockwise encirclement on the origin, alright, it's gonna go clockwise, but however it is negative now, alright, negative 2 in this case, you're gonna go counterclockwise. This is why it's going counterclockwise in this picture right now. It go counterclockwise and encircle the origin 2 times, right? 1 time, maybe I should use a better color. It goes 1 time and 2 times. You see? Bang bang. Very tired. And therefore, yeah, this is it. And the next example, I will not show you how many poles because this is a bit complex. I mean, in terms of complex plane. So for example, this is transfer function. You have 2 poles, alright, because there is no zeros. This is just 100 only. This is some k times 1 over s squared plus 8s plus 32. This one, it comes from here lah, the denominator lah. So only 2 poles, and these 2 poles is in the complex plane because it's a conjugate poles. If you remember, they are in this way, alright. But however, they are not inside this contour. They are not inside. You see, they are not inside. Since they are not inside, and there is no zeros, alright, then we can go by the law stating that, alright, stating that what? the 0, there is no 0, right? Because 0 is there is no 0. Okay, and there is no poles within there, correct? Since there is no 0 encircled in the S contour and no poles encircled in the S contour, this means that there is no encirclement in the origin. In the origin is the keyword, right? So therefore, you see, it didn't encircle the origin. They'll just only go in their own happy stuff, encircling other empty stuff. Alright, it's nothing much. So we are safe in this case, right? And this is the understanding for the application of this equation right here, right now. Alright, but this is not it's not the definition for the Nyquist yet. Okay, so in the next video we shall introduce you to Nyquist. I shall see you there.